So the first speaker of today is Karoline Wiesner. Thanks very much for coming all the way from Potsdam to tell us about the role of unpredictability in the formation and maintenance of complex systems. Thank you.
I guess one thing I'm trying to do in this talk is, as a complexity scientist, I'm trained as a physicist and now I do complexity science. And many people, when they hear that I'm a complexity scientist, they say, oh, you do chaos theory. And then I'm trying to explain to them that those are not the same thing. And in my talk, I will try to explain that here. What are the differences? And also, it's not coincidental and it's not stupid to say, oh, you are a chaos theorist, because there are clear commonalities. If anything, historically, it's not a coincidence that they sort of arose as scientific fields almost at the same time. So to give you a bit of an idea of where I'm taking us, I will start with the history of complexity science, which I see as starting in the 1980s. And I'll just give you one example that sort of exemplifies the excitement that was around at the time, why people thought there is something totally new here at the scientific horizon. And I'll take you from there through, what does it have to do with computation, what does it have to do with chaos, through the concept of self-organized criticality, which some of you might be familiar with, and then from there to actually complexity science, features of complex systems. That's the agenda. Okay. So the term, the edge of order and chaos, that is a term that was coined by Chris Langton in the 80s. And where did he get this idea? So this term was actually picked up by many others because it sounds funky, right? What's happening between order and chaos. So we've been talking about order this morning, we've been talking about chaos. In complexity science, thinks there's something in between which is interesting. And this is a book by Mitch Waldrop, actually the book that I read in the 90s that got me into this because it was so exciting. It's the history of the Santa Fe Institute in New Mexico, where a lot of this theory was developed, or the field complexity science really took off, not least through scientists from Los Alamos, which is just around the corner. So what was this idea? Where did this edge between order and chaos come from? It came from the study of cellular automata. So for those who are not familiar with this is really a simple, you could almost draw it on a piece of paper. It's a set of rules that you apply to a sequence of white and black squares. And the set of rules are, here's one example given at the top. So if you have 3 black squares, then you want to know in the next time step, you want to know what colors they have in the next time step, black or white. You look at the middle one, and the rule is, if both neighbors are black, it's going to turn into white. That's the first rule. Okay. Second rule is, if one of the neighbors is white and one is black, it turns white, and so on and so forth. So you just have a list of rules, and you can apply them over and over again. And if you then do this on your piece of paper, every row, you apply these rules, then you can get patterns. And depending on these rules, completely deterministic rules, you get very different patterns. So the picture on the top is a rule. You can enumerate them from depending on dimensionality and so on. Rule 54 gives you these very regular patterns. Rule 110 gives you also quite regular patterns, but a little bit more interesting. Some of these give you no pattern whatsoever. Some of these give you patterns, well, where you'd say that this looks pretty chaotic. So you can get it all, order, chaos, and patterns. And then Langton came along and he studied this, and he thought, is there some understanding to be gained? Which rule gives you what? Which rule gives you no pattern whatsoever? Which rule gives you totally chaotic stuff? Which rule gives you interesting patterns? And then he went along and took one of these sets of rules. And in this case, what he did is he took a one-dimensional cellular automaton. If I stand here, there's a feedback, so I need to look at the slides this way. And he said, well, my rules are for each square are based on the two neighbors. So that's why I wrote neighborhood 4, 2 to the left, 2 to the right. And then these states, actually, the cells can have more than 2 states, not just black and white, but also, let's say, green and purple. Okay, so it's a few more rules, but you can enumerate them. And then he went along and he defined this lambda parameter. And the lambda parameter is a parameter that says, it's basically giving you the ratio of how often a cell is going to die, which means it's going to turn black. So it's just a ratio that goes from 0 to 1. And based on that ratio, he looks at what patterns do you get. And so I'm going to show you this video where on the top you see a slider, and I'm just picking a few rules, and then see what happens when these rules are applied by this, the simulation is running through this application from the top down. So we're starting here, kicking this off. So rule 81, I think. So we see this is very regular, not terribly interesting, but also not completely dead. This one, after a few applications of the rule, there's no pattern whatsoever. Everything turns black. Turning the slider to the right a little bit more, suddenly things start to happen. So the process is the same, we're just applying rules, but these are different rules we apply. So that looks, what we would intuitively say, interesting, right? Whatever interesting exactly means. And then we turn it further to the right, and here it already becomes hard to even distinguish any pattern in that sense. We would say, well, this now looks like what used to be broken TV screens back when we had TVs. So the further we pull this slider to the right, the further we go to the 1 value of the lambda parameter, then the less structured this image is. And so somewhere between perfect order on the left, perfect disorder on the right, somewhere in between there is something interesting happening. And that's what Langton came across when he played around with these things. And he thought, oh, clearly, there is this in-between is where things are interesting. And you can quantify this to some extent, not least using entropy, which we heard about in the last talk. And when you do that, you really do see something like a spike in these measures, say an entropy measure. You see a spike and that goes back down again. And then he coined this term edge of chaos, where this is not, mathematically speaking, the right-hand side is not chaos, but it is, intuitively speaking, it's chaos because it's randomness. And this edge of chaos, so that got people excited, because clearly there's something there. We know it when we see it. There's no definition yet around what it is, but we know it when we see it because it looks interesting. Yeah. Here's another example which I'm going to show you, which also John Conway came up with around the same time. This is now a 2-dimensional cellular automaton. So we do the same game. We have now cells in 2 dimensions, and we have certain rules that we apply to them. So at each time step, we apply these rules and see how the colors change. Okay? The rules are, again, very simple. So you can summarize them really in 3 rules, which I wrote on the left. So a cell that has exactly 3 cells of the other color next to it will be alive, if you like. And if it has fewer than 2 or more than 3, it's going to die. That's roughly the summary of the rules. If we apply these rules, so let's do that here. So we're setting this up in some random configuration. Then we let it go, and we see immediately, it goes down to a quite well-defined density of living cells. Those are the purple cells. And it's called game of life. Game, not because it's a game, it's a simple simulation following an algorithm, but live because, you see these structures that are, you think things are now calming down, just like Chris's pendulum, this is it. But then, something happens again and it keeps going. And you see these cascades of activity, really. And sometimes you see activity like gliders going through the screen. So this is, these days, this is not exciting. This is no no 2-year-old would think this is interesting anymore. But back then, this was interesting because it was completely unexpected, let alone predicted. Yeah. And this is for one. This is something where it was realized that, if you like, complexity can come from simplicity. We just have these two rules, and out of these two rules, they're even deterministic. Something like this can come around. And if we wait long enough, then this will actually die down to a periodic state. But for now, it's still, as you see, it keeps on going. And there's more to this, and that is a connection to physics was discovered. So now I let this run again, and what I do is I go in with a mouse pointer, and I will randomly switch cells to the different state. So you'll see this in the video, and when I do this, then it sort of becomes a game. So there's my pointer, and now I'm clicking randomly onto these states, and sometimes nothing happens, and sometimes I'm kicking off cascades of activity. Right, so here's a small, that died out. This one starts to actually become a cascade, and so on and so forth. So actually this one you can do for a while without getting bored, especially when there's boring work that's waiting for you to be done. So now here we can start, being scientists, we want to measure something. And this is one example where people thought, okay, what I can measure, for example, is how often do I actually kick off these cascades, and how long do these cascades last? As we saw, some of them are really short, and others actually go on for a while. So that we can do statistics on, and that's what, in this case, I forgot to write the name down, Per Bach, and his team did. They measured how many cascades are we kicking off and how long are these cascades. And what they found is here plotted on the right on a logarithmic, double logarithmic scale, which means that there are very few cascades that last very, very long. Most cascades, die off very quickly. And on this log-log plot, you get a linear relationship. It's pretty noisy, but it's to a good approximation linear. And that is well known in physics and in mathematics. We call it a power law. And this was well known from the physics of phase transitions. So suddenly you had hit on something which was known from physics, but you saw it, a statistical relationship, if you like. You see it in a computer simulation that is just based on two rules. And that really knocked people's socks off, because how come? Does that mean that nature is a computer, or that this computer is nature? Or, suddenly there were really lots of possibilities of how information processing was related to natural processes. So let me explain this a little bit more. Before I do, of course, the famous example here is the sand pile model, which I chose the game of life because I thought it was more illustrative, but the famous example is the sand pile model. And a year before that, farmers work on coupled nonlinear differential equations, which gets us back to what Chris Budd was talking about. So you saw these sort of statistical behaviors in all sorts of systems, not just in this very one game of life. Okay. Oh yeah, here it is, sand pile model. Okay.